There, welcome back. Today we're going to talk about impulse response and transfer functions of discrete and continuous time systems. Okay? All right, so just a quick agenda of what we're going to talk about. First, we'll start out by talking about impulse response in discrete time. Then we'll move on to continuous time. And finally, we'll conclude with a very, very brief overview of transfer function theory. Okay? Now, I just want to stress this transfer function part will be very short. I'll release an optional kind of longer video talking about Laplace and Z transforms if you haven't seen that material before. Okay, let's get started. Okay, so as I set up here, we're going to start by talking about impulse response of discrete time systems. And, before we kind of dive into the specifics of this, I want to take some time just to kind of lay out the approach we've taken so far. Okay, so far, our analysis is focused pretty much entirely on the state equations of the system, right? So in continuous time, right, we have x dot of t equals a of t x of t plus b of t u of t, right? This is the continuous time state equation. And then in discrete time, we have x at time step k plus 1 equals a at time step k, x of k, plus b at time step k, u of k, right? Discrete time state equation. And really, all of our analysis has been centered on these, right? So we focused almost exclusively on properties of these equations. Okay? So what we've kind of shown, right, is that, we have solutions that exist and are unique to these. We kind of examined these things called state transition matrices, which tell us about the structure of solutions to these state equations. And we went through this whole thing, right? But we know what we can also do is we can also define an IO map for the system. Okay? So the IO map really goes much more directly. So directly from your input to your output. Okay? So it kind of cuts out this middleman of the state equation and it just jumps directly from, the input, whatever input signal we pass into the system, to the output signal of the system. Okay? And this kind of hints at a, maybe you could say two-faceted approach to control. Okay? So let me summarize what this is. So two approaches to control. And obviously, I'm using very broad strokes here, okay? So the first approach, which we've kind of taken so far, is the internal or state space approach. All right? And this is the approach in which, we kind of look into the details of the state equation, right? We look at the internal dynamics of the system and we figure out what's going on from there, okay? So today we're going to focus on the external approach. This is sometimes called the input-output or IO approach. And what we do here is instead of kind of peering into the system and examining the inner workings of the state equation, we just go directly from the input signal to the output signal, right? And we evaluate the behavior of the system that way. Okay? So both of these approaches have their merits. They're both useful in different places. And we'll kind of get a better feel for this as we keep moving on through the course. Okay? All right. So with that said, let's kind of return to this problem of impulse response in discrete time. Okay, so let me just provide a real quick review. So recall. And what I'm going to talk about is kind of how we compute the discrete time the discrete time input-output map. Okay, so discrete time IO map. All right. So a couple lectures ago, we kind of built up the tools to derive the discrete time IO map, right? And what you can show is that this IO map is computed rho of k, k naught, x naught, input signal u, equals c at k1, oops, let me just call that k, phi at k, k naught, x naught. Let me start writing this in the next line because it's pretty long. Plus c at k times the sum from j equals k naught up to k minus 1 of 5k, j plus 1, b of j, u of j, plus d at k, u at k. Okay, so this is really split into two parts, right? First, we have this term involving only the initial condition, right? This is called the zero input response, okay? And secondly, we have this term that only involves inputs, right? It doesn't involve any state information. And what this term is called is the zero state response. Okay? So, if we're kind of interested in characterizing the I/O behavior of the system, right, then maybe we don't need to focus on the zero input response, right? If all we're interested in is kind of understanding how the input affects the output of the system, then we could just kind of focus in on this term involving the inputs, right? So the idea is in the I/O approach, we'll focus on the zero state response, right? Because that's the term that involves all these different input values. Okay, now here's an issue. The zero state formula that I wrote above is really quite complex, right? It took me 2 lines to write out, and we got all these different terms floating around, okay? So what we're going to do today is we're going to figure out what structure underlies the zero state response, okay? So we're going to look for more structure, and we're hopefully going to simplify the study of the zero state response. Okay, so there's this really nice, powerful idea in linear systems theory, and that idea is that in order to completely characterize the zero state response of a system, we actually only need to know the response of the system to a single input function, okay? And that input is something called the unit impulse. Okay, so what we'll see is we only need to know response to an impulse. Now, once we know this response, we can kind of construct the response to any signal out there. All right, so first I'm going to go ahead and define what a discrete time unit impulse is. So definition, discrete time unit impulse. So the discrete time unit impulse is the signal. It's a discrete time signal, so I'll write it with these little square brackets. It takes in an integer, z, and maps to r, and it's defined as follows. So delta at time k, excuse me, let me write this as a delta actually. So this is the letter we usually use. So delta at time k is equal to 1 if k is equal to 0, and 0 if k is non-zero, okay? So the discrete time unit impulse signal is the signal that jumps up to 1 when k is equal to 0 and is equal to 0 everywhere else, all right? So we can actually define a shifted version of this as well, and this will sometimes be useful for us. All right, so the shifted impulse is the signal delta superscript k naught, which still maps from z to r. And this signal is simply defined by shifting the standard unit impulse, okay? So this is defined delta k naught at time k equals delta of k minus k naught, all right? Where k naught is some fixed integer value. All right, so the shifted impulse, instead of jumping up at time 0 and then being 0 elsewhere, it jumps up at time k naught, okay? So this signal will actually be able to characterize our response to any input out there, all right? So our goal is to kind of work our way towards this result as we go on. Okay, so now that we've defined the discrete time unit impulse, we can define the response of the system to that impulse, right? So next, we will define the response to an impulse. Okay, so I'll go ahead and start in the SISO case, and then I'll generalize to MIMO afterwards. That brings me to the following definition, which is the discrete time impulse response map And this is, remember, in the SISO case, right, where we have single input and single output. That means that our input value spaces are, and our output value spaces also are. So what I'll say is, consider a SISO discrete time linear I/O system, right, one of our formal abstract dynamical systems with I/O map rho. Okay? The impulse response map, right, this is what we're trying to define. The impulse response map is the map H, which takes in two integers, so it goes from Z cross Z, and it returns a real number. It's defined as follows. So H at K, comma K naught, is defined as rho of K, K naught, 0, delta K naught. And this is if K is greater than or equal to K naught, and then it's 0 if K is less than K naught. All right? Okay, so let's go ahead and kind of summarize what this definition is saying. All right? What this tells us is that the SISO case, the impulse response map is equal to the response of the system from 0 initial state having an impulse applied at time step K naught. Okay? So in summary, it's the 0 state response to an impulse applied at time K naught. Okay? So just as a quick side note, due to causality, right, which tells us that the present behavior of our system only depends on stuff that's happened in the past, we have K minus K naught implies H is 0, right? Let me quickly justify why this makes sense. So what we're saying here is that H is meant to be the response of the system from 0 initial state to an impulse applied at time K naught. Okay? So if we're not applying anything before K naught, which we're not, by definition of this delta function over here, and we're starting at 0 state, then it makes sure that we should be kind of at 0 state all the way up until the time at which we apply this delta. Okay? So if we don't do anything and we need to start at 0, then we should kind of be at 0 before we start. Okay. Very nice. All right, so now let's go ahead and generalize this definition to the MIMO case. So definition, impulse response map of a MIMO system. Okay, so this is multi-input, multi-output. So now I'll say consider a MIMO discrete time linear I/O system with I/O map rho, input value space Rm. Okay, so our input values are going to be m-dimensional tuples of real numbers. So input value space Rm, output value space Rp. The I/O map, the impulse response map of the system is now the map capital H, still takes in two integers, right, Z cross Z, but now maps to a matrix, all right? It's going to map to a matrix in Rp by M. We're going to define this as follows. So H of K, comma K naught is equal to this big matrix. We'll have H11 of K, K naught. If we keep going all the way over here, what we'll end up with is H1M of K, comma K naught. If we go down here, we will have H P1 of K, comma K naught. And if we go all the way over here, we'll have HPM of K, comma K naught. All right, so this entire matrix is filled up. All right, and yeah, this is in R P by M. Okay, so how are we actually defining each of these entries? Well, what we'll have is Hij of K, K naught, which equals little hij of K, K naught, is defined as follows. This is defined as the ith coordinate of the impulse response to an impulse applied in coordinate j of the system. Okay, so what it is I take my I/O map rho, I evaluate it at time k from time k naught, initial state 0, and an input which is a shifted impulse, delta k naught, applied in the jth coordinate, okay, where ej represents the jth standard basis vector of Rm. All right, so I take this, and then I find coordinate I. Okay, so what I have is that the impulse response map of a MIMO system is a matrix-valued function where entry ij represents the effect of an impulse applied in input coordinate j on output coordinate I. Okay, so entry ij tells me how input in j will affect output in I. Okay, fantastic. So how are we actually going to calculate this thing? Well, remember, earlier when we kind of wanted to get concrete about these, kind of very abstract dynamical systems, we turned to linear system representations, right? So now what I'm going to go ahead and do is I'm going to show how you calculate the impulse response map for a linear time varying system representation. Okay, let's do that. So proposition, impulse response map of a discrete time linear time varying representation. Okay, so I'll say consider a linear time varying representation A, B, C, D. Okay, now the impulse response map of the system is computed as follows. So we'll have h of k, comma k naught, is equal to the following case-by-case function. So we'll have ck, phi of k, k naught plus 1, b at k naught, in the event where k is strictly greater than k naught, okay? We'll have d of k in the event where k equals k naught. And finally, we'll have 0 in the case where k is less than k naught, okay? So we have 3 different cases to evaluate here. All right, so in order to prove this, what are we going to do? Take a moment to think about this. Okay, so I'll assume you've taken a moment to think about how we might go about doing this proof. And, maybe what you came up with is we're going to take the IO map of a linear time-varying representation, and we're going to see how coordinate I of the IO map changes when we apply a unit impulse in coordinate j. Okay, so let's go ahead and do this. So what we'll do is we'll take an input signal u, which is equal to an impulse applied at a time k naught in input coordinate j, all right, where ej once again represents the jth standard basis vector. Okay, so if I go ahead and compute the IO map using that formula we kind of remembered earlier, we'll have rho of k, k naught 0, u coordinate I will be equal to c at k sum j equals k naught up until k minus 1, phi of k, j plus 1, b of j, u of j, plus d of k, u of k. All right, coordinate I. All right, so what I'm going to do now is I'm going to go ahead and substitute in this delta k naught times ej. Remember, we have 3 different cases to verify. Okay, so let's start with case 1, which is the case of k greater than k naught. All right, well, in this case, what are we going to have? Well, if k is greater than k naught, then u at time k will be equal to 0, right? Because this impulse is only equal to 1 at time k naught. All right, so what we'll have is that rho, these arguments, is, we take coordinate I of that, is equal to c at time k. And then if we look at this entire sum, right, our input is 0 except for when j equals k naught, right? So we're just going to pick out that value from the sum. So this is equal to c of k times phi of k, k naught plus 1, b of k naught, and then u at time k naught is just going to equal to ej, all right? And then the second d term drops out because for k greater than k naught, our input will be 0, all right? We'll take coordinate I of this. All right, so what's going on here? Well, here what we have is that the vector ej is actually going ahead and it's selecting column j from this matrix over here. And then we say from column j, we want row I. All right, so what we're really asking for is entry ij of this matrix that I've just highlighted. Okay, so C of k, phi of k, k naught plus 1, b of k naught, entry ij. All right? And we confirm that is in fact what we wanted to show above. Okay, fantastic. So let's go ahead and try the next case. So for case 2, we're going to examine k equals k naught. And in this case, what we'll have is row of the same arguments above, coordinate I, will now equal to what? Well, now if we evaluate it k equals k naught, this sum is going to be empty, right? Because our top index of our sum will be lower than our bottom index. So that entire sum term disappears. What we're just left with is d at k, u at k, all right? Which in this case is equal to, oops, I'm forgetting my coordinate I here, d at k multiplied by ej, coordinate I, which by the same reasoning as above is equal to d at k, coordinate ij. Okay? So that goes ahead and that completes the second case for us. Okay, so case 1 is done, case 2 is done, and then case 3 of k less than k naught, we just immediately define it as 0, okay? And this is just by definition of the impulse response. Okay, fantastic. So we've proven this result. So what are we going to do now? Well, remember, our whole kind of goal in undertaking this whole process was to really simplify the study of input-output analysis, right? So we wanted to come up with some really nice, clean formula that will mean that, we don't have to use this really long, messy formula for the impulse response map, or excuse me, for the IO map, okay? So a key step in doing this is to recognize that we can write any input as a sum of impulses, okay? So key step in simplifying IO analysis, we could represent any signal out there just as a sum of impulses, okay? Let me state this in the following lemma. So lemma, let me call this signal representation via impulses. What this says is consider a signal, let me call u, which goes from z greater than or equal to some k naught, right? So all integers greater than or equal to some integer k naught, and maps into Rm, okay? So what I'll say is for all k greater than or equal to k naught, u of k is computed. U of k equals the sum from j equals k naught up until k of the shifted delta, delta j at k, u at j, or alternatively written j equals k naught up until k of delta k minus j, u of j. Okay? So this might seem a little bit obvious if I write it out, right? Because this delta function here is only equal to 1 right at the value that we need, right? Right at time step k. So this just goes right ahead and it just picks out the input value that we need, okay? So even though this thing seems a little bit obvious, it turns out this is actually going to be a really useful formula for us, okay? So it's trivial, but very useful, right? So proof that just follows from the definition of delta, right? Delta is equal to 1 when you pass in 0, and is equal to 0 elsewhere. Okay. So let's go ahead and kind of apply this formula, all right? Let's show that this thing is actually useful for something. So I'm going to state the following theorem. What the following theorem does is it uses this lemma in conjunction with the definition of impulse response to say that we could represent the response of a system to any input out there using our impulse response map. Okay, so this is super powerful. So theorem, which I'll call zero state response via impulse response map. Okay, so here's the statement. I'll say consider a discrete time linear system with IO map rho and impulse response map H. Okay. So for an input signal U defined on Z greater than or equal to K naught into Rm, we have the following. So we have rho of K, K naught, 0, input U, right? For an arbitrary input U is actually defined via the impulse response map. Okay, so we can actually calculate this using H. So this is equal to the sum from J equals K naught up until time K of H of K comma J, U at J. All right. So this tells us that our impulse response map actually entirely characterizes the zero state response of the system. Okay. So if we look at how nice and short this expression is, this is a huge simplification over that really long formula that we had earlier. Okay. So I just want to make one quick remark before discussing the proof. So what I want to say is that in lecture 1, we defined the input space U to be the set of all sequences, right, from Z into Rm. This is for a discrete time system, okay? But here, what I've given you is a signal from Z greater than or equal to K naught into Rm, okay? So this and this don't quite match, right? The signal that I've given you isn't actually defined on all of Z. So technically speaking, this isn't actually something that our formal I/O system can accept, right? So to get around this problem, we introduce the following convention. All right. So when given a signal U, which goes from Z greater than or equal to K naught to Rm, we identify it, which means we treat it as the exact same thing as the extended signal, U extended from Z to Rm, which we define as follows. So U extended at K is equal to U at K, right? If K is greater than or equal to K naught, which is the domain of definition of the original function U, and then if K is not greater than or equal to K naught, this thing is just equal to 0, right? So it's equal to 0 if K is less than K naught, all right? So this is a really harmless identification to make, right? We're just saying wherever our given signal is not defined, just set it equal to 0, okay? So I just want to stress, I'm not going to write out UE, all right? I'm going to automatically identify this signal U and UE. So if I give you a signal U and it's defined on Z greater than or equal to K naught, then I start manipulating it as if it's a signal on Z. You could assume that I've extended it in this manner. Okay, fantastic. So with that said, I just really want to quickly discuss the proof of this, all right? So the proof of this result turns out to be a simple consequence of the representation lemma, which we discussed above, which says we could write any signal as the sum of these unit impulse functions, and it's a consequence of linearity. Okay? So literally all you need to do to prove this is just combine linearity of the I/O map for this linear time-varying discrete time system with this fact over here, which says you can write your signal as a sum. Okay? So all that we're saying in this formula is that UJs are simply going to be kind of scaled up impulse responses. Okay? So, or excuse me, scaled up impulse signals at each time J. All right. So you can go ahead and check the details of this if you want. It's a kind of nice exercise to try. But just for the sake of time, I'm not going to do it out in full detail here. Okay, very cool. So let's summarize. Our main takeaway is that we can write output, or excuse me, the zero state response of a linear I/O system to any signal in terms of the impulse response. Okay, so this is really nice. This gave us a huge simplification of our original formula. Okay, now what we're going to do is we're going to specialize to the LTI case. All right, so you might remember earlier in the class, we found that when we specialize to LTI from LTV, we learn a whole lot more about the structure of our system, right? For instance, we discovered all of these facts about the matrix exponential and all this fancy stuff when we switch from LTV to LTI. Okay, so let's go ahead and do this now for this discrete time case. What are we going to find? Well, there's a basic idea, which is kind of nice. And that idea is that in time invariant systems, time past is the relevant quantity, right? So you might remember this from lecture 1. So time past is the relevant quantity, not the objective endpoint times. Right, so you might remember, that these LTI IO maps are maps that are invariant under shifts in time, okay? And this is essentially what we're saying over here, okay? So what should we expect this to mean in the context of the impulse response map? Well, if I have an impulse response map and I compute it at times k and k naught, what should I expect? Well, the impulse response from time k to k naught should be the same as the impulse response over the difference between times k and k naught, right? So we should expect this thing to be equal to k minus k naught 0, right? Because remember, all that matters in an LTI system is the amount of time that has passed, okay? Not the objective times k and k naught, right? Just the difference. All right, so this fact kind of tells us that all we need to care about in an LTI system is the first argument of this impulse response map, okay? And this observation kind of leads us to the following special notation, which I'll just state as a definition, okay? So definition, which is the LTI, discrete time LTI, impulse response map, okay? So I'll say consider a system, an LTI system with impulse response map H, which takes in 2 arguments, right? This goes from Z cross Z into the space RP by M. So this was what we defined for the linear time varying case, right? Now I'll define the linear time invariant, right? So this is a special impulse response map. The linear time invariant impulse response map is the map H, which now only takes in a single argument, right? A single value in Z, still goes into RP by M. And this map is defined H at time K is equal to your 2 argument H at K, K naught. Okay? So all that we do is we just remove the second argument, all right? And when we remove the second argument, we declare it to be an LTI impulse response map, all right? So quick remark, this is a little bit of an overload of notation, right? So we're using H for both of these, but depending on whether you're using 1 argument or 2 arguments, it should be clear from context, okay? So it should be clear from context which map we're talking about. All right? And remember, we defined it this way because in LTI systems, time passed is the only quantity that matters, okay? So if you want to compute something like H of K comma K naught, you would just plug in K minus K naught into your impulse response map over here. Okay. Okay, now that we've described this discrete time LTI impulse response map, we can just go ahead and compute it for a discrete time LTI system representation, okay? And fortunately, this will just kind of follow directly from this formula that we derived above, okay? So we already kind of proved that this is the case when we have a linear time varying system. So all that we need to do is substitute in the discrete time state transition matrix, okay? This formula is really going to follow immediately. So a nice corollary of this earlier result is for an LTI system representation, which is specified as a tuple A, B, C, and D. What we have is that your discrete time impulse response map is computed h of k equals ca to the k minus 1 b when k is greater than 0, d when k equals 0, and 0 for k less than 0. Okay? So you proof, just substitute in phi of k, k naught, equals a to the k minus k naught. Okay? And we're just going to apply this with k naught equals 0, right? And that immediately gives us this result from what we had proven earlier. All right, fantastic. So far we've defined this new discrete time LTI impulse response map. We computed it in this LTI case, but we haven't really shown what further simplifications this thing yields us. Okay? So let's kind of study the output equation. Let's see how it simplifies further. So how does the output, let me actually be more specific. How does the zero state response simplify, right? Given all of this nice new information. Well, let's go ahead and compute it using the formula we derived above. So we have rho of k, k naught. I'll just go ahead and define it for time 0 for convenience. Okay? So rho of k, 0, 0 state, and an input signal. Earlier, we proved that this is equal to the sum from j equals 0 up until k, right, of h of k comma j, u at time j, right? And now using our discrete time LTI our discrete time LTI impulse response map, we can rewrite this guy as j equals 0 up until k, h of k minus j, u at j. All right? Now what we'll do is we will assume, using that convention that we established above, that u of j equals 0 for j less than 0, right? If our signal isn't specified, then we just assume it's 0. And then this guy is equal to the sum from minus infinity, right, up until k, of h of k minus j, u at j. And then since h of k minus j is 0 when its input is negative, we can actually extend this upper bound to infinity as well. Okay? So if j becomes too large, then that'll just drop out to 0. So we could just automatically extend that to infinity. Okay, so what we've derived over here is actually something called the convolution formula. All right? So sums that kind of look like they're of this form are super, super important in control and signal processing and all these other fields. Okay? Let's just go ahead and formally define what we kind of derive loosely up here. So definition, convolution sum. So I'll say consider signals u and h of compatible dimension. Okay, compatible dimension just means I can multiply them, okay? Like there's no size issues. All right. And these signals should satisfy the product, h of k times u of k is an element of RP, okay? Then the convolution of h and u, which is defined h star u, and this goes from z into RP, is the signal, which is defined as follows. So h star u evaluated at time step k equals sum j equals minus infinity to infinity h of k minus j u of j. All right, just exactly that sum that we had described earlier up. Okay, so this is the convolution of h and u. Now it's important to note convolution, let me write this in red, convolution of two signals is a signal, not a value. Okay, just as another quick side note, we'll use the word convolve to describe the action of taking the convolution of two signals. Okay, so what we're saying here is if we convolve h and u, we should get another signal. Okay, not a single fixed value. Okay, fantastic. So let's kind of rephrase some of our earlier results in terms of the language of convolution. So earlier, what we had said, right, is that u at any time k is equal to the sum from j equals k naught up until k of delta of k minus j times u of j, right, when u is specified on z greater than or equal to k naught into Rm, okay? But now, we recognize that due to properties of delta and, due to our convention of saying u was going to be 0 before time k naught, we could extend both of the bounds on this sum, right? This goes from minus infinity up until infinity, delta k minus j, u of j. Now, what's this but the convolution, okay? So it turns out u at time k is actually equal to the convolution of delta and u evaluated at time k, okay? So there's this really interesting property of this discrete time delta function that it actually gives us an identity under convolution, okay? So we get an identity. All right? Now let me just quickly state another corollary of our earlier results. This is essentially just going to be what we had derived up here, just stated in formal language, okay? So what we had showed above is that for an LTI system with an IO map rho, what you have is rho of k, k naught, 0, and u is equal to the convolution of h and u, okay? Where h is, your LTI impulse response map, okay? It's going to be evaluated at time k. All right, fantastic. Oops. Let me just change this to a 0 over here. Okay, fantastic. So at this point, we've pretty much finished up our study of the discrete time impulse response, okay? So we can move on to our second point for today, which is the continuous time impulse response. Now, I just want to quickly point out, a kind of observation about how we've structured this lecture, okay? So you might have noticed that, usually what we do in these lectures is we start in continuous time, and all the way at the end, we kind of specify how these results, kind of translate over to discrete time, okay? But here we've done the exact opposite, right? We've started in discrete time, and then we've said, okay, we're going to take a look at continuous time afterwards, okay? So you should be a little bit suspicious that I did this, all right? And the reason that I did this is that it's actually pretty hard to define a continuous time impulse response and do it rigorously, okay? So what we're going to do in this section is we're going to give a semi-formal treatment of the continuous time impulse response, okay? When I say semi-formal, I mean we're going to be a little bit hand-wavy here and there, but I'll be kind of precise in my hand-waviness, okay? So I'll do my best to specify, when I'm making an assumption that's maybe not quite mathematically rigorous and when I'm being a little bit more rigorous, okay? So what we're going to do is we're going to use the discrete time impulse response as a template for the continuous time case. All right, we'll kind of look for continuous time analogs of all these different structures that we evaluated in the discrete time case. Okay, so in order to define a continuous time impulse response, kind of the first thing that we need is some notion of an impulse, right? So we actually need a continuous time impulse signal. All right. So this was that nice unit pulse function that jumped up from 0 to 1 in the discrete time case. Now we need an analog for continuous time. All right. What I'm going to argue is that the key property of the discrete time impulse was the representation lemma, right? Which told us we can represent any discrete time signal as the sum of discrete time impulses, okay? So let me just write out what this was. So we had u at time k was equal to this infinite sum, j equals minus infinity up until infinity, of, what was it? Yeah, that's right. So delta k minus j times u of j, right? This is what we showed above. Okay, well, we know this is equal to the convolution formula, right? Delta star u, excuse me, of k. So in other words, what we'd like to do is we'd like to find a continuous time signal and a continuous time notion of convolution that kind of give us these same properties, right? If we have those, then we'll kind of be on track for mirroring this discrete time case, all right? So it kind of looks like in order to define this continuous time delta, what I'll first need to do is define a continuous time notion of convolution. All right, let me go ahead and do that. So definition. Now there's this kind of basic principle in math. Whenever you switch from something that's discrete to something that's continuous, usually you'll kind of swap out a sum for an integral. All right, and that's really exactly all we're going to change here. So convolution integral. Okay, so I'll consider signals u and h, which are now continuous time signals of compatible dimension. Remember, that just means that we can multiply them, where their product, h times u, is going to be a member of Rp, okay? So kind of same setup as before, now just with continuous time signals. So we'll define the convolution of h and u is the signal h star u, right? Same symbol as before. And it goes from R into Rp. It's defined as follows. H star u of t equals the integral over R. Now, when I write integral over R, I just mean the integral from minus infinity to infinity. It's going to be the integral of h of t minus tau, u of tau, d tau. Okay? So as a quick side note, this really has the same structure as this discrete time formula, right? We have something of t minus tau, and then something at tau, right? And instead of having an infinite sum, we just have an infinite integral. Okay, so this is a pretty natural translation of convolution to the continuous time domain. Okay, fantastic. So now we have our continuous time candidate definition for convolution, right? We can kind of go ahead and figure out what the signal delta might need to be in continuous time. All right, so our goal is to now look for a signal delta such that delta convolved with u at t is equal to u at t, right? That's the same property that we had before. In other words, delta t minus tau, u of tau, d tau, integral over r is equal to u of t, right? And this should hold for all, I'll just call it for now, sufficiently regular, right? So this kind of means piecewise continuous, sufficiently regular inputs. Okay, cool. So what is this function delta, right? So maybe you kind of sit down and see if you could kind of think about some of its basic properties for a moment. I'll give you a moment to think about that. Okay, so I'll assume you gave it some thought. Now, here's a problem. This is a really big problem, actually. Such a function cannot exist. All right? This is a really big issue. Okay? So what you can show is, as a consequence of this definition, such a signal delta of t needs to be 0 almost everywhere. Yet, at the same time, you could also show that the integral of delta over r would need to equal 1. Okay? Now, these two facts can't both be true, right? This guy up here implies that the integral of delta equals 0, right? Because something that's 0 almost everywhere needs to integrate to 0. Yet, we also require that the integral of delta is 1, okay? So we have a contradiction if we define a function that does this. Okay, so this is a really big issue, right? Big issue. So we can't find the function delta from R to R that gives us what we need. Okay, and this is kind of really quite problematic, right? Because without an impulse, we can't really define an impulse response, okay? So what are we going to do? So there's a couple things we could do to kind of remedy this problem, all right? Now I'm going to outline what our approach will be and then kind of an alternate approach that you could take, all right? So potential solutions. It turns out that giving an actual rigorous answer to what delta needs to be involves the theory of distributions, okay? All right, so this is approach 1. And then approach 2 is you can use something called approximations to the identity. The basic idea of this approach is you approximate delta with a special class of well-behaved signals. And these signals are called like delta epsilon, okay? So they're parameterized by a real number epsilon. And essentially when epsilon goes to 0, you get the convolution behavior you want in the limit, okay? So this is like a particularly nice class of functions that kind of approximates what this delta wants to do, okay? So there's a brief exposition on how you use these approximations to the identity in the notes, okay? If you're interested, I suggest you check it out, all right? It just involves a little bit of analysis. But what I'm going to do is, right now in lecture, I'm just going to give you a very small flavor of what this distribution theory is like, okay? So I'll be kind of informal here, right? I'm not going to have a fully rigorous definition. I'll just kind of give you a watered down definition of the distribution. Okay, so it turns out the kind of distribution that we need is called a Dirac delta distribution. So let me give you an informal definition of the Dirac delta as a distribution, okay? This is not a function. So definition, which is informal. This is called the Dirac delta, okay? So what I'll say is let E be a subset of the set of functions from R to C, be a vector space of functions, functions called the test functions. Okay? So what I do is I define the Dirac delta on this set E as a linear map delta, which goes from E into the set of complex numbers. It's equipped with an operation star, which I'll call convolution, such that the following properties are satisfied. So first, we'll have a property which I'll call origin, all right? So if delta takes in a function f, which belongs to this set E, then it should return f at 0, okay? So this should hold for all f and E. Now, second, what we'll have is the impulse property. This is the big one, the one that we were really kind of looking for. So delta convolved with f at time t, where this convolution operation is this special idea of convolution that comes along with this special distribution, okay? So delta of f, evaluated at time t, is equal to f of t, should hold for all t, and for all f and e. Third, we have linearity, which states that delta and its operation convolution should be linear, okay? So delta convolved with alpha f plus beta g equals alpha delta convolved with f plus beta delta convolved with g. And finally, our convolution operation should be associative, okay? So we should have delta convolved with f convolved with g, where this guy is just the standard integral definition of convolution. This should equal to delta first convolved with f, then convolved with g. All right? This should hold for all fg belonging to our set E. Okay, so what I've done over here is I've essentially taken the essential properties of a delta function that we want, right? And I've kind of abstracted them away into this very formal idea of a distribution, okay? This Dirac delta distribution, all right? So this is not a function of time, right? The Dirac delta is actually a map on a space of functions, all right? Because above we proved we cannot have a function of time that gives us what we want, okay? So we need to look for a map on a different space. So this is a map from a space of functions called test functions into the space of values of those functions, all right? And we define a couple of basic properties that really make it behave exactly like this delta function that we want, okay? So that's all that we've done here. We've just abstracted away the properties that we want into this new map on a function space. Okay. So just like we defined the shifted delta function in discrete time, we can kind of do the same thing in continuous time, right? So what I'll do is I'll define the shifted Dirac delta as the function delta t naught, which maps from E into C. And this takes delta t naught, function f, to f of t naught, and delta t naught convolved with f, valued at a time t, equals f of t minus t naught. Should hold for all t and for all f in E. Okay, and all the other convolution properties should also follow. Okay, nice. So let's just summarize real quick, because this is kind of a hard concept to grasp, right? So what we proved, or kind of reasoned about earlier, so we showed there can be no function of time delta from R to R giving us what we want. So our solution to this was to generalize. Okay? Instead of looking for a function of time, we looked for a generalized signal or a distribution. Okay? Which is a map on a space of test functions. All right? Satisfying some special properties. Okay? And using this abstraction of a distribution, we were able to get a delta that actually gives us what we want. Okay? So we found functions of time were not cutting it, right? If you define delta to be a function of time, you immediately run into a number of contradictions, right? So instead, what you're forced to do is to generalize to this more abstract notion of a distribution, which instead of a function of time is a map on a function space into the space of values of those functions, okay? Satisfying some regularity conditions. So I just want to highlight this definition is still informal, okay? This is not a fully rigorous definition. This is not a fully rigorous definition for a Dirac delta distribution, okay? If we wanted to sharpen this up, we would need to add a little bit more structure to this set of test functions E. Typically, you kind of assume that E is the set of C infinity functions with compact supports, or another kind of sufficiently regular set like that. And we would need to make sure that this operation of convolution generalizes well to other sorts of distributions, okay? So there shouldn't be something that's just sort of kind of specific to the Dirac delta, all right? And then there's a couple of other regularity conditions that we need to check. But this definition kind of gives you a flavor for what the actual formal definition might be like. Okay, so let's kind of figure out how we actually use this Dirac delta in practice, okay? So here's what I'm going to say about using the Dirac delta. Distribution theory is quite hard to study and motivate, okay? And as a consequence of this, what you'll find is that in a lot of books or I don't know, other text in the field, people will often manipulate a delta function as if it were a function of time, okay? Which we know is false, right? We know it cannot be a function of time. It's actually truly a map on a function space. But, sometimes this is something people do, okay? People often manipulate delta as if it were a function of time. Delta of t, okay? Remember, this is not rigorous. But, just because it's not rigorous doesn't mean that, it can occasionally be a useful tool to kind of, give us some insight into problems, okay? So, just because this is something that you might often encounter if you go ahead and you read another book in linear systems, I just want to kind of lay out a couple of basic ground rules for how you would manipulate a delta if it were a function of time, okay? So I'm going to state a very informal proposition that tells you how these delta functions are used as functions of time, kind of commonly in the field, okay? So I want to stress this proposition is not mathematically rigorous, all right? If you want to interpret the statement of the proposition in any way, you should just interpret it as special notation, okay? Remember, this is just notation to communicate an idea. It's not something that's mathematical fact. Okay, so proposition, which I want to stress, is informal. And I'll call this rules, in quotes, for treating delta as a time function. Okay, so what I'm going to do is I'm going to take a signal u in PC of r, comma r. Now for all times t at which this signal u is continuous, we have u of t equals the integral over r, right, equals in quotes, of delta of t minus tau, u of tau d tau. Remember, delta is not truly a function of time, but, for convenience, this is how people often write it, okay? U of t minus t naught equals the integral over r of the shifted delta, delta t naught, t minus tau, u of tau d tau. This is if continuous at t naught, right? And then if u is continuous at 0, then what you might find is that u of 0 is equal to the integral over r of just delta integrated directly against u. Okay, delta of tau, u of tau, d tau. And then if it's continuous at your time t naught, then you'll find u at t naught equals the integral over r of your shifted delta, delta t naught, time tau, u of tau, d tau. Okay? So I want to emphasize these are not mathematical facts. Okay? Just think of these like notation. So just notation to communicate the abstract properties of delta. Delta in the language of signals. Okay? So you should never use these formulas in a mathematically rigorous context. Okay? Just think of them as helpful notation that'll kind of give you insight into what the delta function is doing. Okay? Just because, we're very familiar with signals that are functions of time, and this kind of helps us reason about things. All right? So we can kind of rigorously motivate each of these formulas with these approximations to the identity. All right? If we use these approximations to the identity, we could kind of say that, in the limit as epsilon goes to 0, we kind of get these properties showing up. Okay? So if you're interested, you could go check that out.